great.
Oh, somehow my daughter's name is on the screen. I don't know why that is.
That's very nice. May I, before I let Kajiwara take the chair, may I remind everyone to mute your microphone unless you are the speaker. If you wish to ask questions during the talk, you can, I guess, step in if Peter doesn't mind, or write your question in the chat box. And I hope Kajiwara-san will be able to announce the question at the appropriate time. So, and also please turn off your videos because that helps with the bandwidth for the communication during the seminar. So I'll now hand back to Kajiwara-san. Thank you.
Thank you very much. So good morning, or I should say good afternoon. And so today's speaker is Dr. Peter van der Kamp from Trobe University. And title is Integrable Maps from Reduction of Lattice Equations and as Generalized Manin Transformations. So Peter, please start.
Thank you very much. This talk has two parts. I will give a bit of context about lattice equations and their properties, where they come from, and then how you can reduce them to a mapping. And there's a way of doing that called periodic reductions, which has been done since the 90s and is fairly standard by now, I would say. And one thing, what you want to do there is when you take a lattice equation that is integrable, you want to use the integrable properties to derive integrable properties of the reduction, the mapping. So I'll show you how that works. And then I'll proceed on to open reductions, which is the discrete analog of what Cheng was talking about last APIOS seminar, where you basically have your lattice equation on a half lattice with a boundary. So in the second part, then I will try to understand what we get. So if we do a reduction, we get a mapping, and we want to understand what is the mapping like in a geometric way. And we do that by intersections of curves and pencils. And I will give an introduction to a quick overview of what Q or T maps are, Manin transformations, generalizations of that. And in particular, there's one mapping that we found through open reductions, which led to kind of a new type of Manin transformation with involution curves. So that's an overview of what I'm going to talk about, and let me get into part one. I don't mind being interrupted for a question. I'm pretty easygoing with that. So what is a lattice equation? Probably most of you know what that is, but I'll give a bit of context anyway and where they come from. So it's a very simple equation. There's one given here. It's called H1 in the ABS classification. This is a classification of lattice equations that are consistent around the cube, which I will explain on the next slide. Jan, can you mute your microphone? And maybe some others as well. Thank you. So where do these equations come from? They're very simple, multilinear, just a relation between 4 points on a lattice, and this relation extends to the whole lattice. So these hats and tilde notation, they mean shifts. So hat will go up and tilde will go to the right. Not sure if I'm pointing to the right for you if I do that. But we can therefore shift kind of this whole equation, and we get an equation between u tilde hat, u tilde tilde, and u tilde hat. And on the lattice, we have the point u tilde hat here, So that equation that is kind of tilted there is an equation on this square connecting those points. So this equation, where does it come from? It is the Bianchi permutability for the Backlund transformation of a continuous equation. So if you start with this equation, a famous Korteweg-de Vries equation, or the potential form of that, and you have a solution, you can put that solution here on your lattice. You can create a new solution by using a Backlund transformation, which is a system of ODEs, and it has a parameter. So we're using alpha, we create a new solution, and we can use the same Backlund transformation to create another solution if we use another parameter. So beta is here. And then we can start with those solutions that we have just found. We can do the same thing again. So we can start from the solution U tilde, use the Backlund transformation beta to get to U tilde hat. And we can use the Backlund transformation with alpha to go there as well. And the thing is that we get, we have commutativity, so it doesn't matter in which order you apply these transformations. And that is the Bianchi permutability. And there is this relation between all these solutions, and that is the quad equation. So that's where it comes from. Now what we have on the lattice is these parameters, alpha and beta, and they form kind of a characteristic line. So we have this characteristic line for alpha, and we have the same characteristics line for beta. If we have more complicated quad graphs, we have more of these lines intersecting and weaving through each other, and this can all be posed on higher dimensional, embedded in higher dimensional cubes due to consistency. And that is my next topic, and that is what is understood as the integrability of this equation on the discrete level. We can pose this on a 3D cube, and that is drawn here. So on the front face, for example, if we replace all the heads in the equation with a bar, we get the following equation: U minus U tilde bar multiplying U tilde minus U bar is equal to alpha and beta. And this would be an equation that is then satisfied on the front face of the cube, and on every face of the cube we have such an equation. And that leads to three ways of calculating, for example, this point. If we start with U bar, U tilde, sorry, U hat and U tilde, we can use the front face equation to calculate that quantity here. Then the side face on the left to calculate this quantity, the bottom face to calculate that quantity. And then we have three ways of calculating this quantity, either from the right face or the top face or the back face, and all three have to be equal. And then we say that this equation, or this system of 6 equations, is consistent around the cube. That implies multidimensional consistency, so this cube can be embedded in higher dimensional cubes, and restrictions of that will give you quad lattices or quad graphs. Now, this 3D consistency gives you a Lex pair. We can calculate the quantity U tilde bar in terms of U bar as a fractional linear transformation, and that fractional linear transformation can be expressed using a matrix, and that is your Lex matrix. So this will give you a linear system. So we have some kind of, we can linearize that fractional linear transformation. So we get a psi vector tilde equals L psi, and then the consistency, or with the other equation for psi hat, will give you the relation that is here at the bottom. It's just a product of two matrices being equal to a product of two matrices, and it is expressing going around the cube in two different ways. Now, I want to stress a nice interpretation of this relation in terms of the characteristic lines. We can halve the cube in two different ways. We can look at the front half of the cube, and then we have the front face and the right face, and we have a characteristic line running over that in this way. Then we have another characteristic line running over the front face and the top face, like that. And we have another characteristic line running over the top face and the right face, like that. Not sure why that disappeared. There we go. And we can do the same on the back of the cube. So let me take another color. So we can go over the back of the cube like this. This is the bottom face and the back face. We go over the right face and the back face like that. And then we go over the left face and the bottom face like this. And the particles all are characteristic lines. This is the, maybe you can think of it as a particle. This is the second one, and that is the third going there. And you see they interact in a different way. The green one, we have the first interaction between 1 and 2, and then interactions with 3. And for the blue one, we first have the interactions with 3, and then 1 and 2 interact after that. So that's a nice interpretation of this consistency and how the characteristic lines, it doesn't matter kind of how they run through each other. Another thing I want to stress is there is an element of scaling. So if you go from Mobius transformations or fractional linear transformations to this matrix representation, you have a scaling that you have to fix. And the scaling can be fixed for this matrix in such a way that L U bar multiplied with LU by U is equal to some constant, and that constant can be scaled to 1, which is something that is makes it easy to do proofs. You may want to not scale it to 1 and work with square roots for reasons to get nicer invariants later. But this is something that we have been working hard on in a recent paper with Cheng and Coudrelier. And there we kept a little bit of freedom in the scaling for good reasons. Maybe last thing I say is that we started with a Backlund transformation for the continuous equation. This cube also has an interpretation as a Backlund transformation. So if you look at the equation at the bottom, the equation on the sides, you can view them as a Backlund transformation for the same equation on the top. So now kind of the circle is round, where we started with Backlund transformations for the continuous equations, and we ended up with Backlund transformations for the discrete equations. So that's a bit of context, and now I want to show you how you can reduce these equations to maps. And the first thing we need to do is think about initial value problems. So if you just look at putting these equations on a lattice, then any staircase provides an initial value problem. A staircase is just any line that goes over the edges of the lattice from any diagonal line from top left to bottom right, or bottom left to top right, whatever you want.
Sorry, Peter.
Yes.
I got a chat question from Bajanov.
Okay, it wasn't sent
to everyone, so I'm going to read it out.
Yes.
Question to speaker. Is there anywhere a relation to Liouville integrability?
Definitely, yes, yes. that's a big topic of this talk. We will get there in a minute. So Liouville integrability is a notion for maps. So what I've talked about here is for lattice equations, the integrability of lattice equations. Once we go from the lattice equation to a map, what we basically want, we want to use the structures from the lattice to prove the Liouville integrability of the map. So, and we are in the process now of going from the lattice to the map. And this slide is kind of an explanation of that. We start with a staircase, and this is as the standard staircase is kind of a straightest line. If you are restricted to edges, then this is the straightest line in that direction that you can draw. And then what if we want to do this reduction, we have to take periodic initial values. So we set the initial values as x1, 2, and 3, and then we repeat that on this staircase. And this way, we can calculate the fourth value of x by just using that relation on this square, the blue square. And you can go on. You can calculate x5 here by using this square quad equation. And the relation to get to x5 from x4, x2, x3 is exactly the same as the relation to calculate x4 from x3, x1, and x2. So this will give you a map, and you can continue mapping this and filling out every value on the lattice. So this is a three-dimensional map. If we add 2 and the absolute value of 1, we get 3. So every kind of A, B staircase will give rise to an A plus B dimensional map. And what we know is that we can form a monodromy matrix, which is the product of matrices over the staircase. So in this case, we would take a product. It's an inversely ordered product. So we go L, 1, 2, then L from 2 to 3, and then L from 3 to 1. And that is the monodromy matrix in this case. And what we then have is another matrix such that this holds. So the product of the monodromy matrix with M is M, the same M at the same point, times the shifted monodromy matrix. So n is the new variable, the index on the x, on the initial values. And you see you can multiply from the left with m minus 1, and that will give you basically this statement that the trace of the, if you then take the trace, that will be an invariant of the map. It does not depend on n anymore. So this is a way to produce invariance of your mapping. This, and you know, if you take a long staircase, you get very high dimensional mappings. There is this parameter in the Lex matrix, lambda, which connects to the kind of third lattice parameter, where you go up in your 3D cube, and you can expand your trace in powers of lambda, and every coefficient will give you an integral. Now they don't need to be independent necessarily, you have to check that, but this would give you enough integrals for Liouville integrability. And here is this. Yes. Is there a question? No. So in this example that we looked at, we get this invariant. Just for illustration, it's very easy. Product of 3 2x2 matrices, take a trace, and there you go. What I want to now look at is quad graphs with boundary. So these are very natural objects. You take any surface with a boundary, take a cellular decomposition of that surface, you take the dual of that graph that you have, you combine them together in what is called the double and that will give you a quad graph where every face has 4 edges, so something like this. And the boundary very naturally is a boundary of triangles. The question is, how can we pose equations on such a thing? So we know the quad equations. Can we come up with triangle equations? And what does it mean to be integrable for such systems? And this was started by work of Cheng and Vincent and oh, I'm going too far here. Wait a minute. Here we go. Kamp, Caudrelier, and Zheng. They started this in 2014. And here is the answer. What you should have is a compatibility condition that is very similar to consistency around the cube. But in this case, we have half of a rhombic dodecahedron. And the consistency is that if you start with the black dots, X, U, and Y, you can use all the equations that you have. For example, on the boundary equation on the bottom face, you can calculate Z. Then you have a quad equation where you can calculate V. On the left, the what else? At the back, there is a quad equation where we can calculate W. We can, at the front, we have an equation from X and U, we can calculate R. Now we can use that quad equation there in front of you to calculate S from V, U, and R. And then we have 3 equations to determine T, namely a quad equation at the back, a triangle equation at the top, and a triangle equation at the back. Note there is no quad equation here on the boundary. There is no equation there. So only 3 equations to calculate T, but that's enough. Requiring that all the values are the same, that is a consistency condition. And they claim that that is a good consistency condition. We should take that as a definition of integrability of boundary equations. And that was a very smart idea. Here it's the same diagram but flattened, so it's really not a 3-dimensional consistency condition. It's 2-dimensional. Here you can easily kind of do the same calculation, calculate V, R, Z, then W and S, and 3 ways of calculating T. It's maybe a bit more visible in this picture. And here are some examples. So this equation here on the slide with alpha and beta as parameters, quad equations called Q1, 0. 0 relates to a parameter delta that is set to 0. And there can be several boundary equations that are consistent with one quad equation. So here are some examples. There are more. We can have a sigma, which is an involution that relates the parameters. So if we look at characteristic lines, and actually that's something I forgot to say. Let's have a look at it now. What is the meaning of this diagram? If we look at characteristic lines, let's go here on the front. We bounce off the boundary and we get out of the diagram. This is on the front half of the half rhombic dodecahedron. And there we have another characteristic line. So we can bounce here and get out of the diagram there. If we now look at the back of the half dodecahedron, we can do the same thing. We can go in here, bounce off this boundary, follow all the quads at the back, or we can go in here, but now we go through the back, we bounce here, and we get out there. So here is the same ID. This is the first characteristic line. This is the second one. And what we see here is that it doesn't matter whether we first get an interaction of the characteristics line and then the bouncing, or we first get a bounce from the first particle and then an interaction and then the second bounce of the thing. So this is the characteristic line ID, which is very similar to the characteristic line interpretation of the consistency around the cube. All right, so and it also shows that the parameters need to be related. So alpha and beta, if we have this bounce on the boundary, beta needs to be related to alpha by an involution, and that is because if you look at the bottom triangle, we have that beta is sigma of alpha, but then at the top we have that this should be the other way. Somewhere it should be the other way around, that alpha is related to beta by sigma as well, and therefore it needs to be an involution, because if we just close the two halves together, then the characteristic lines are loops. So we need that involution there. Okay, and there's two types of involutions. This is the multiplicative one. There is also a additive one, which is that sigma of alpha is what is it, 2 mu minus alpha. And there are boundary equations there as well, but I have not got them on the slide. Now here is a new idea, that boundary equations have duals. So boundary equations have a couple of properties, and they are fractional linear, or multi-quadratic relations. They have some kind of symmetry where if I interchange the, for example, in this quad, if I interchange x and z, I should get the same relation with alpha and beta interchanged. And there is a non-degeneracy condition. And the thing is that if you combine a boundary equation and the equation on the quad, you can eliminate one of the variables and you get a new relation. And if that relation has the same properties as the relation you started with, then we call that a dual equation. And if we have such a dual equation, then in fact we have the same equations on the other half of the square. So if q is here, we have q here as well. And if q star is here, we have q star here as well. And the important thing of dual boundary equations, here is just an example what the duals are, but is another consistency condition. So this is a truly 3D consistency condition, unlike the previous one, and it's called dual boundary consistency. So here we have one equation, q, on this triangle in the middle here, and we have q star on these ones. And you can start with x, y, and u, and you can calculate all points using all the equations on the quads and the triangles, and there will be two ways of calculating that point E here. And if they lead to the same value, we have a consistency condition. And the thing is that this consistency condition is equivalent to the previous one. So the consistency condition for the ordered pair q, q star to be consistent is equivalent with q being boundary consistent according to the previous consistency condition. In all cases, we have seen that q star is also boundary consistent, but it does not seem to follow from the proof. You really need to interchange Q and Q star to get that result. And this leads to a Lex representation. So we can get a K matrix, a boundary matrix, in precisely the same way as we got the L matrix. Namely, you can express, for example, here you can express E in terms of S as a fractional linear transformation, and you can convert that into a matrix, and that is your boundary matrix. So if you do that, you have to use Q star to get the boundary matrix for the equation Q. And that solved a bit of a puzzle. But now we have Lex representation, we've got everything, we know integrability, and the only thing we now need is a initial value problem to get to mappings. So here we go. If we take two boundaries that are parallel, and we take as many squares in between as we like, we get an initial value problem. And it is clear that this leads to some kind of involution on this lattice, this strip of the lattice, we could call it. And you know, we can start calculating, updating on the triangle on the left boundary. We can calculate this point. We can use all the squares to calculate these points. We can calculate the point on the left boundary, and then we can also use all the squares, again, the quads, to calculate these points. And then we have shifted kind of this initial value, all the initial values, one step to the top right, and that is a mapping X to X prime. And there is also an associated mapping between the lattice parameters. Now, there's one easy way of getting rid of this mapping on the parameters. Namely, we can take all the parameters on the horizontal edges to be the same, let's call it alpha, and all the lattice parameters on the vertical edges, we can take that as sigma alpha, where sigma is that involution that is related to the boundary equation. So then you get rid of that transformation between the parameters, and you have an autonomous map, an n-dimensional map. Now, what we did before with periodic reductions, we had a monodromy matrix, and the trace of that gave us integrals for that map. The same thing can be done here. Here is the double row monodromy matrix. So we take a product of Lex matrices from the top boundary to the bottom boundary. Then we multiply with that K matrix, the boundary matrix at the bottom. We go back from the bottom to the top boundary with a product of all, inverse product of all the Lex matrices. And when we're at the top, we take another matrix connected to the equation on the top boundary. That is the double row monodromy matrix. What we can prove then is that there exists a matrix such that this is the case. We have a few constants in here. So F relates to constants if you don't scale all your matrices so that the inverse matrix will give you 1. You get this F in there, and there are good reasons to have that. And that epsilon, that is something that is, I forgot to say, but that is here in this relation. So sometimes we need to take epsilon to be 1. Sometimes we need to take it -1. And that epsilon does appear in this statement here. And it means that if we take a trace of the double row monodromy matrix, we either get invariance or we get anti-invariance, or 2 invariance. And if you take all your parameters arbitrary, you include that non-autonomy, this mapping of the parameters, then we might need to take the n-first iterate of the map to get an autonomous map, and in that case the trace will give you n-first invariance or 2 n-first invariance. But these can all be kind of, if you take high enough iterates, you get invariance out of this. So this provides a way of taking open reductions, open meaning we have boundaries there, and yeah, maybe this is as opposed to closed. If you think of what you do if you take a periodic reduction, then basically you roll up your lattice, so it's kind of closed, the monodromy matrix. Now here is one example that I want to share with you. We take this equation Q1 that was on the slide before. We take n is 3, we do the reduction, and we take the square of that so that we really get integrals, and we introduce some reduced variables, and in these variables we get a map of the plane, and we get an invariant cubic pencil that is left invariant by this map. So what does this mean? I have a picture for you to show you what the map is doing and what this invariant cubic pencil is. There's a parameter here, so we have two functions. The map depends on A and B are just parameters, and C is an arbitrary constant. For every C, we get one curve in the plane. And in this picture, I have some curves, drawn some curves. Each curve has its own color, and there is one curve in black. And if you start with 1 point on that black curve, you apply the map, you get another point. So we apply the map to this point, for example, and we get to that point, we get to that point, we get to that point. Now we want to understand what is happening. Why? How can we think of this map and understand it more geometrically, what it's doing? So we can calculate it. Yes, all these points lie on a curve, but what is it? So this brings us to part 2, and we want to understand more generally integrable maps of the plane, preserving a pencil of curves. So we have two functions. They can have degree 2, 3, 4, anything. And what we want to do is understand this as compositions of two involutions. It's actually a theorem that any integrable map of infinite order preserving a algebraic curve should be a composition of involutions, but it's generally a hard problem to really decompose a map into its involutions. And involutions, how are they defined? There are some classifications of involutions of the plane, but we are going to look at the involutions as intersection of curves. And to do that, I need you to know a few things. I need you to know what a base point of a pencil is, and Bezout's theorem. So if we have two curves, then these curves intersect in the product of their degrees points, and we should count intersection numbers with multiplicities. So I'll be working in just normal coordinates, finite coordinates, or I'll be working in P2 if I have points at infinity. Yes, what is a base point? Well, let's just have a look at the picture. A base point is a point where every curve goes through. So it's a point that is on that curve for every single value of C, in that pencil for every value of C. All right, let's start with a very simple example of how can you define a map by an intersection of curves. Start with a linear pencil of lines. So x minus y is c. It's the simplest thing I could come up with, except that this has a base point at infinity. So all the lines are parallel. So that's similar to saying there is a base point at infinity. That's where they intersect. And then here is another, here is a curve, a conic curve. And that conic curve has the same point at infinity. So each line of the pencil will intersect this curve at the point at infinity. And then we know that, you know, a line and the conic should intersect in 2 points. So that means we have 1 point at infinity and there is only one more point left. We can calculate that point and that will give us a map. So if we map every point to that point of intersection, we get this map. And that's kind of the simplest thing that I can think of how you can define a map defined by the intersection of a pencil and a curve. And this has a nice interpretation because this map, you also find this map if you look at the evolution of the probabilities of autosomal inheritance involution. So very quickly, an individual has either autosome DD with capitals or small letters, and it inherits these properties from its parents. So if you know all the probabilities of the parents, you can calculate the probabilities of the children. And this is exactly how these probabilities evolve. So this map is just a map from the probabilities of the parents to the children, and you can iterate that map. And now the surprising thing is that if you iterate that map, you stay where you are. After one breeding step, the probability is fixed, and it's set in so-called Hardy-Weinberg equilibrium. And here we see the geometric reason of why this is fixed, because, you know, we're going to the intersection, and if we start at the intersection, we go to the intersection that you stay where you are. So no need to iterate this map to find out that you stay where you are. By definition, this is kind of satisfied. All right, that was a bit of a sidestep. Let's now go to integrable maps. The first type of integrable map is the QRT map. And this is the case where the pencil is of degree 4. But it's a special pencil. It's a pencil where the degrees in X is 2 and in Y also 2. And that means that we can solve, if we know one X, we can solve for the other X. So we can fix Y and define a map by taking a straight line. This will have 2 intersections, and we can interchange those intersections. And that will give you an involution. And that's called the horizontal switch. You can do the same for the vertical switch. You can take an arbitrary point, look at which curve is this point on. You look at the other curve, which will be somewhere here, that it's on, and that's your vertical switch. And by combining these 2 switches, you get a map that preserves this pencil of curves. And this is called the QRT map. And that is an 18-parameter family of integrable maps of the plane. It also preserves a measure, and it is a kind of famous integrable map of the plane. Manin transformations, what are they? This is where we have a cubic pencil. And a cubic pencil has a number of base points. And if we take one of these base points, a simple base point, and we take a, so for example, this one, that is a base point of the pencil. We fix that. And we now define an involution by saying, okay, well, take a point on your, in the plane. What are we going to take as the image of that point? Well, take this straight line through that base point and through the point that you took, and then look at the other intersection of that straight line with the curve that the point is on. We know there's only going to be one, because in general there will be three. One we started with, this is the base point, so there's one other one. So now the map, the involution, is going to interchange these 2 points. And that works for every point in the plane. For every point in the plane, there is a curve. That curve will go through this base point. So for every curve, there is one other point, and that is the image of that point under the Manin involution. And the composition of 2 Manin involutions is a Manin transformation. And again, that's an integral map because it is measure preserving as well. We can generalize this idea by taking singular curves of higher degree. So this is again a degree 4 pencil, but it's a special pencil. This pencil has singular points, and there are 2 singular points here. There's one here and another one here. You can see that it's singular because every curve goes through that point twice. And that means that if we take those points as involution points for some kind of generalized Manin transformation, then the intersection of a straight line through such a point only has 2 intersections with the curve. So in general straight line, degree 4 curve, there's 4 intersections. There's already 2 in the involution point, so there's 2 left, and the involution will interchange those 2 points. So that's a generalized Manin transformation, but only for special singular degree 4 curves. We can apply the same idea for degree 2 curves. So these are conic sections. Here is an ellipse, for example, and the point P, you can take that as an involution point. And then the point A is mapped to B by the involution, and B is mapped to A by that involution. Again, you take 2 involution points, you combine the involutions, you get a map. But in this case, there is no restriction on the pencil, and also no restriction on the point P. It doesn't have to be on the curve, it can be anything, because any line just intersects that conic in 2 points. And there is another special thing here, namely that if you take another point on the so-called Pascal line, which is the line through PQ, then that will be a reversing symmetry of the map. Now, I won't go into further detail, but it gives rise to infinitely many symmetries of these maps preserving conic curves. I want to talk about work from Petrera, Surisway, and Zander. They defined a new kind of Manin involution. So instead of using a straight line to interchange points, they constructed a whole pencil of curved lines in such a way that each curve in that pencil intersects the curves in the pencil you start with in 2 points precisely, so that you can interchange those 2 points. So what I've drawn here is 3 curves of that quartic pencil that I had before, and these are given in red, blue, and gold. And I've drawn a pencil of quadratic curves, and some of them are here in green, yellow, and gray. And if you take for example, a point on the blue line, the blue curve in the quartic pencil, Now you can just follow the green line to see where is the other intersection of that green line with that blue line, and it happens to be here. There are a few more intersections, but they will be at base points of the pencil. So this is constructed in such a way that the pencil of curves that are these quadratic curves, they have the same base points as the original pencil of quartic curves. And the curves that, the points that are there are rightly here. So 4 points will lead to a unique pencil of quadratic curves, and you can use that pencil to define an involution. And this generalizes the idea of Manin transformations, where the pencil V was a linear pencil of points with one base point. Now, what I want to do is understand this map gamma, also in terms of Manin transformations. But the Manin transformations, if you look at the action of the map on one curve of the pencil, then it's just a Manin transformation. So we can think of this map as a composition of two involutions, sending first involution, sending this point to that point. Then the second involution, there's another involution point there, sending that point to that point. And that is then one iterate of the map as a composition of two involutions. And that works fine on this particular curve of the pencil. However, that point is not a base point of the pencil. So it will not work for any other curve of the pencil. What is happening here is, whoops, that went a bit too fast, is that for each curve, there is a unique point on that curve, which is then the involution point for this, this second involution. And if you connect all these involution points, you get something that I coined an involution curve. And the special thing about this involution curve is that there is only one non-base point intersection. So this is very similar to what we saw before. We can construct this curve by making sure that this curve has only one non-base point intersection with every curve in the pencil. So let's do a bit of counting. The pencil, the cubic pencil, has 6 base points. There is one base point at 0, 0, another base point at 0, -1, and I took that one as one of the involutions, to create one of the involutions. There are 2 infinitely near base points at infinity, and there is 2 more base points at infinity of that pencil of cubic curves. Now that conic, that is the involution curve, intersects each curve of the pencil in B0, B2. B2 is the point near, B2 prime is the point near B2, and B4. So if we now count the intersection, we have 1, 2, 3. That is a singular point, so it has intersection multiplicity 2. If we add that all up, we get 5. But we know the conic has degree 2, the pencil has degree 6, so that is 1 more. There must be 1 more intersection. And in this case, we can actually calculate that intersection. This point C is the parameter that selects the curve in the pencil. And in terms of that parameter, you can calculate that unique non-base point intersection. And if you calculate the involution defined by the Manin involution, taking this as your involution point, then you get exactly the second involution that is that in the decomposition of this map gamma. And this actually led me to just a general definition of what is an involution curve. And that is here an involution curve for a cubic pencil. So this only works if the degree is 3. cubic pencils, if the intersection numbers of that curve Q with any curve of the pencil at the base points of that pencil add up to 3 times the degree of Q minus 1. So how is that involution defined? Well, we have to define how, if you have your kind of involution curve Q, you want to know how IQ acts on a point P. What you have to do is you have to look at the curve in PC that goes through P. Then you look at the intersection of that curve with your involution curve, and then you take the straight line through that point. So this is P, this is Q, and then the involution IQ will interchange P and I, and that is how your involution is defined. Now, this is not a new thing. The Bertini involution is an example of such an involution. This is kind of a classic involution constructed over 150 years ago, I guess. And in this one, we have a degree for a curve, which is the involution curve, and it is constructed in such a way that B0 is a triple point and all the other points of the pencil are simple points. And now you can just add 3 and 8 and you get 11. So that is 1 less than 12, which is 3 times 4. So that all makes sense. This is an involution curve. The special thing about this one is that if you look at the tangent at the triple point, and you can see that in the pictures, that will intersect each curve in the involution point. So the fact that this tangent is right, you know, goes through the intersection of the green curve and the red curve at the unique non-base point intersection, that's a very special geometric coincidence theorem. Last, some open problems. Conjecture, I'm claiming that the involution IQ with the involution curve Q that preserves a pencil of cubic curves is anti-Measure preserving with density 1 on F. This is the case for, you know, every single involution that I have created, but I don't know how to prove it. So some work to do here. You can maybe ask yourself, you know, how many of these involution curves are there? So the idea is that for every degree M for singular pencils, there are exactly 2, and for non-singular pencils, it seems to grow linear, but exactly how many there are is also still an open problem. I will show you some references. The first one is good for periodic reductions. It's not the first one, definitely, but there's references in there. The first paper about boundary consistency is by Coudrelier, Crampet, and Zhang. Then we have a new paper about these integrable boundary open reductions and the maps that I talked about. You can read more about Manin transformation in the other references here. I will stop here and maybe there is time for a few questions.
Thank you very much.
You're welcome.
So are there any questions and comments, please? So
there's a raised hand from Bajana.
Yes, yes, please.
Yes, so just a moment.
Yes, Professor Bajanov, please.
Yes, so what's the relation? So given the integrable map, which satisfies the consistency around the cube condition, it's not clear how to define a Hamiltonian structure. So the motion is a canonical transformation. Even discrete motion there should be a canonical transformation of a set of canonical variables. And in this approach, it's not clear how to, in principle, find the structure.
Absolutely, you're right. So it's clear in certain cases we can construct symplectic or Poisson structures for certain reductions of certain lattice equations. It can be done, and it has been done. But in general, it's not clear. You're absolutely right. It's you know, it's an open problem, but I doubt that someone will solve it very soon. Can be done in special cases, but I don't know how to do it in general.
Well, there's a few years ago with Sergeyev, we proposed an approach to do that, but not much has been done. But if you start with quantum integrable system, which classified mainly by quantum groups, affine quantum groups, so you automatically have Hamiltonian structure from the beginning.
Oh, that is
And
nice.
in the cases we studied, it always reduces to some classical, consistency around the cube equation. So in all examples we considered, we get consistency around the cube in the limit. And so we automatically get Hamiltonian structure. So that, I think the example we considered reduced to H3.
Okay. Yeah. If you say it lifts, I would say it lifts to H3, right? Because the reduction goes the other way. You start with the lattice, you reduce it to a mapping, but in your case, you would lift your mapping up to a lattice system or a consistent system. Is that right?
Yeah, but no, it's somehow embedded automatically in the structure, so you don't have to do anything. So if you have local evolution equation, they can be reduced to H3.
Okay. Yep. Thank you for that.
Okay. Are there any other questions or comments? Okay, so the time is now 12 o'clock, 1 o'clock for you. So let's finish, let's close the session. So thank you very much, Peter, and thank you all the participants.
You're welcome. Thanks for organizing.
Do you have anything to say? Yes.
Thank you very much, Peter. That was a lovely talk.
Thank you.
So I guess we can close the recording and the transmission.
Yes.
Thank you everyone for coming.
Oh.